Let's take some time to focus on the different types of structures in organic chemistry. And so far we have focused on looking at converting a molecular formula to a dot structure, but we also want to explore a hybrid of the two, so-called structural formula, as well as an abbreviation style frequently used in organic chemistry called the skeleton structure. Let's start with one example, propane, which has the molecular formula C3H8. Now, probably one of the easiest ways to think about developing a dot structure that fits this formula would either to use the models or to simply start by connecting all the carbons together. Remember, carbon makes 4 bonds, and hydrogen only typically makes 1, so that the hydrogens in a structure are always going to be decoration that are added to a structure rather than a central or bridging atom. You should never have more than one line drawn to a hydrogen atom in one of your dot structures. And the novelty of drawing out all those individual lines and bonds quickly wears off, and so we have a couple of shorthand ways of drawing that molecule. First, a structural formula, where we will write something of a hybrid between the molecular formula and the dot structure. So notice that we have a C with 3 carbons, and then a C starting with 3 hydrogens. The next carbon in the row has 2 hydrogens, and then we come to the end of the row, which again has 3 hydrogens. So to write the structural formula, we'll write the carbon, the number of hydrogens directly attached to that carbon, and then the next carbon, which has 2 H's, and then further down the line, so we have a total of 3 hydrogens. Now the way we draw a so-called skeleton structure is to use, and we can actually draw dots to represent carbons, but what we're going to do is have the end of a line, a bend in lines, and intersections of lines represent carbon atoms with enough hydrogens to give those carbons 4 bonds. So when we draw a dot structure that looks basically like an upside down shallow V, what we're implying is that at the end of the line and at the bend in the line, each of those positions there is a carbon with enough H's to give 4 bonds. So here we have 1 bond shown. That would mean we're lacking 3 bonds. We're to assume that there's 3 hydrogens. There'd be 2 in the middle and 3 on the other end as well. Now let me give you a structural formula that has more than one possible isomer or way of connecting the atoms such that all of the bonding conformations are normal bonding conformations of each element are followed. So we'll say C3H8, and then we'll add an oxygen to the formula. Now, if you want, you can work on dot structures. That's a good place to start for practice, but you'll notice that the novelty quickly wears off. So see if you can draw at least 2 different isomers. There are, in fact, a total of 3. If we think about starting with simply a carbon backbone, if we put all 3 carbons in a row, one option would be to put the oxygen on the end. And then if we then we can flesh out this structure with hydrogens to give all of our atoms their normal bonding conformation. Now notice that this means that the carbons should have 4 bonds, which means that the one on the end gets 3 hydrogens, and then the two that each are connected to 2 other things get 2 hydrogens, and that the oxygen, like water, should have 2 bonds and 2 lone pairs. And so that would be one of our isomers. If we wanted to convert that into a skeleton structure, remember we'll be using dots for each carbon atom. So we'd want 3 dots, and we typically like to use a zigzag pattern. And that will also connect them. And then on this dot, which represents the CH2 here, we would add an OH. Sometimes we'll put lone pairs on the oxygen, sometimes not, depending on the needs. But in this case, we'll just leave them off for simplicity's sake. Now, the structural formula here, following the same pattern we did here, notice all we've done is replace the hydrogen on this end with an OH. And so what we'll end up with for a structural formula is CH3 for this part, and then a CH2, another CH2, and the OH. And in the structural formula, we're not obligated to put lone pairs, and so we don't bother. Another way that we could arrange these elements would be to put the 3 carbons in a row and then put the oxygen on the center carbon. If we then flesh out each atom with the appropriate number of hydrogens, note we need 1 in the middle here, then we'll find that we have still the right number of hydrogen atoms, 1, 2, 3, 4, 5, 6, 7, and 8. And that once we put the lone pairs on the oxygen, we have a complete dot structure. And if we wanted to draw the structural formula, we have a couple of options here. We can write the CH3 at one end, then put the CH and then the CH3 on the other end, or the right side, and then come up to the top with the OH. And that's probably one of the most clear methods. Another way we could actually write this, by the way, would be to note that we have an hydrogen attached to an oxygen on a CH that has 2 CH3s attached. And that's a little less clear, but it fits all on one line. To draw the dot structure here, we're going to start with the same 3 carbon atoms in a row, and we're simply going to attach the OH to the center carbon. Now, do you know what functional groups each of these molecules belong to? They're both alcohols. And by the way, we will call these 2 molecules that have the same formula but different structures isomers of each other. And we'll later refer to them as constitutional isomers. which of course implies that if there's more than one kind of isomer, and that this is just one of them. So at any rate, these are constitutional isomers. Now let's make a little more space and see if we can come up with the last isomer of C3H8O. Thinking in terms of connecting atoms, what we can do is start our carbon chain and then insert the oxygen in between two of the carbons and then continue the chain. Notice that this means we would then need to fill out our carbons with hydrogens, but that the oxygen wouldn't get any hydrogens in this case. So it's not an OH group, it's a different functional group. Our structural formula here would then be CH3, CH2, oxygen, CH3. The skeleton structure, we've got a carbon, we've then got our oxygen, and then we have one more carbon. Connecting those dots, and it would look something like this. And the functional group in this case would be an ether. We have an oxygen flanked by a pair of carbons. Now try some of the practice problems in your textbook that deal with interconverting structures, and be aware that this is something that, while we won't be tested on a whole lot directly, is something that we need to be able to be fluent in doing to understand the other conversations that we'll have in organic chemistry.